So our last topic to go through is the actual regression. If we know there's some kind of linear correlation, how can we come up with this line to estimate our data? So ultimately, given a collection of paired simple data, the regression line is the straight line that best fits the scatter plot of the data. So the word best is very subjective, but essentially we're going to use a process called least squares regression. So you might also hear the regression line be referred to as the line of best fit, or you might hear it as the least squares line. When you use Excel, this is the process that it's using to figure out what is your best fit line. So what we need to do is we need to come up with the equation of our line. So if you remember, in general, lines have a format y equals mx plus b. This value of m is the slope, and this value of b is the y-intercept. So for us, the regression equation, which is just that line, is given by, we're going to approximate our y values by some initial value b0, which is mimicking our y-intercept, plus some slope times our x value. So this x is going to, this b1 is our slope, and this b0 is the y-intercept. It's just slightly backwards, but again, you can switch the order of these. So this particular equation is going to describe our regression line. In terms of vocabulary, this x is the thing that we're inputting into the equation. So that is always what's known as our independent variable. But here also, because we're using this to make some prediction, this is often also called the explanatory, the predictor, or the independent variable. So the explanatory variable, the predictor variable, or the independent variable. You can hear it called any of that. And then y hat is going to be our estimate. So this is either called our response variable or our dependent variable. Where our true equation in the regression line is going to be in the form y is equal to, instead of b's, we use beta. So some initial beta value b0 plus beta 1x. Okay. So what we're going to have to do is figure out, given that data, how can I figure out what b0 and b1 are? Once we do that, then we have the equation of our line and we can use it to make predictions. So ultimately, one thing that does happen is this slope is going to be the same sign as that correlation value. Because remember, if you had an R value of a positive value, you had an equation that looked like this, or a line of best fit that looked like this. If your R value is negative, there was a negative correlation and you would have a slope going downward. So that value is going to match the R. But however, the R value is not the slope itself. So again, we're going to go through an example where we are going to calculate the values of B0 and B1 by hand, but we're going to utilize technology to our advantage because Excel is going to do a lot of these things. So starting out with just our notation, we have a lot of the same ones from finding the correlation coefficient. N is the number of pairs of sample data. The sum of x means we're going to sum all x values. The sum of x squared means we sum all x squared values. Then when you put the parentheses and then square, this means you sum all x values. Then you square it. Sum of xy is all sum of xy values. So you times x and y first, and then sum it up. And then x bar and y bar, remember that bar is representing the mean. So this is going to be the mean of all the x values given. And then y bar is the mean of all y values. Now that we have the notation for each of these, B1 and B0 depend on that. Before you can find B0, you have to find B1. So this formula is n, the number of samples, times the sum of xy, minus the sum of x, times the sum of y, and then this is divided by n, times the sum of x squared values, minus the sum of x values squared. So at least a little bit nicer than our correlation coefficient, because then it doesn't involve square roots, but still a lot of work that we have to do. So this in particular is going to give us the slope of the least squares regression line. Again, there are other ways to figure out what the slope and the y-intercept are. We are specifically using the least squares regression method, and that is what Excel is using when it creates trend lines. Now, once you have B1, then you can go through and find B0, which is that y-intercept. This is going to be the mean of all the y values minus this coefficient we found B1 times the mean of all x values. So this is the y-intercept of the least squares regression line. So we are going to go through and we are going to do this by hand and actually come up with the equation of a regression line. But then I will show you if we do Excel, you end up with exactly the same thing. So we're going to use the given data to find exactly that. So ultimately here, my x values go from 0 to 16. So if you count these up, that's 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11 data values. So I'm going to start out by finding that, writing it down. Our n is equal to 11. I at least don't need to go through as much. I need to find all of my x squared values, and then I also need to find all of my xy values. And then afterwards, we're going to sum these up. So I'm going to need another row down here, add a little bit more room. This will be the sum of my x values, the sum of my y values, and then here will be the sum of my x squared values, and this is the sum of my xy values. Okay, so starting out with x squared, my first value is 6, and 6 squared is 36. 7 squared is 49, 8 squared is 64, 9 squared is 81, 10 squared is 100, 11 squared is 121, 12 squared is 144, 13 squared is going to be 169, 14 squared is 196, 15 squared is 225, and last but not least, 16 squared is 256. Now I need to take all x times y, so we're just going to multiply these pairs. So starting out, 6 times 4.29 is going to give us 25.74. 7 times 5.62 is going to give us 39.34. 8 times 6.72 is 53.76. 9 times 7.58 will give us 68.22. 10 times 8.23 is 82.3. 11 times 8.64 is going to be 95.05. 12 times 8.83 gives us 105.96. 13 times 8.78 is going to be 114.14. 14 times 8.52 gives us 119.28. 15 times 8.02 is 120.3. And finally, 16 times 7.29 will result in 116.64. Okay. So now that I have all of these filled out, I need to sum up each of these columns. So starting out, if I sum up all of these X values, you should see that you get 121. If I sum up all of these Y values, that's going to give me 82.52. Now summing up these square values, that's going to give us 1,441. And then finally, the sum of all X's times Y's is going to be 940.72. Okay. So again, you can use Excel to also fill in this table. You can have it calculate each of these things for you. And then we can go ahead and sum that up. And then we can also even find B1 easily using Excel. So just cheating a little bit, I'm going to go ahead and copy my formula for B1 down here. So we have found all of these values. Our value of N is 11. The sum of X and Y is 940.72. The sum of X's is 121. The sum of Y's is 82.52. Then we need to sum or divide by 11. The sum of X squared is 1,441. And then we need to subtract the sum of X's squared. So this, I'm going to trust you can plug into your calculator. You should get this is about 0.3. So let's go ahead and use Excel just to verify we do get the same values. If I want to do X squared, I'm going to go ahead and hit enter, and we're going to take the X value and square it. So you can times it by itself or use that caret to get the 2. To get X times Y, I have to do equals X times Y. Now I want to sum up all of these values. So at the bottom, I'm going to do sum, and then we're going to go ahead and put in those values. And then same thing here. If I sum up my Y values, I should get 82.52, which I do. Summing up X squared values gives me 1,441. And then finally summing all of the XY values, we indeed get 940.72. So if I want to find my value of B1, what that's equal to, I'm going to put some brackets to do my top, some brackets to do my bottom, because you see it's going to yell at me, but that's okay, because I need to make sure that I'm putting all of parentheses so I know I take this minus or divided by this. So I need to take N, which is 11. I need to times that by the sum of XY, which is this. Then we need to subtract the sum of X's times the sum of Y's. And then in the denominator, this is going to be N times the sum of X's, sum of X's squared, which is that one. And then we need to subtract the sum of X's to the second. So doing all of that, See, it's a bit of a pain. Yep, that's great. Let's try doing parentheses instead of these brackets because my iPad does not seem to like the brackets. So here's the top one, and then here is the bottom, and that already looks nicer and fantastic. We get our value of B1 to be equal to 0.3. Now that we have B1, we want to find B0, but before we can find B0, we need to find both the mean of the X values and the mean of the Y values. But at least you don't have to do a ton of work at this point, because to find the mean of the X values, you have to sum up all the X's and divide by 11. But we already summed up all the X's, that's 121. So 121 divided by 11 gives us a mean X value of 11. To find the Y mean, we sum up the Y's and divide by 11. The sum of the Y values is 82.52 divided by 11 gives us 7.5018 roughly. So our value of B0 is going to be the mean of Y minus B1 times the mean of X's. So this is 7.5018 minus 0.3 times 11. So this roughly to 2 decimal places will give us 4.20. So ultimately we are set. We now can figure out what the regression line is. And that's going to be Y hat equals B0 plus B1X. So our Y values we can estimate by 4.20 plus 0.3x. So again, not going to force you to do this by hand. Instead, we're going to go through and show you how you can do this with Excel, because you can do it directly on your scatter plot. So we've got our XY values. We're going to highlight them, go to Insert, click our scatter plot. Then you click all of the data and just click Add Trend Line. It's going to bring up a bunch of stuff. So just click Display Equation on Chart, and then you move it around so you can see it a little better. So one thing to kind of notice, if you look at the actual data itself, it doesn't really look like it would be estimated by a line well. It's got that curve to it. So realistically, you might find that this has linear correlation, but based on the scatter plot, something else would probably be best fit. So depending on what information you have, will tell you what to use as a predictor. So if you know that there is significant linear correlation between the two, then absolutely we're going to use this equation of the line to predict other values. So I might need to know, what is my approximate value when my X is 10.5? Well, then I would just plug it into this line, Y equals 0.3x plus 4.20. And that would give me an approximate Y value. But based on this look, this line is not going to be a good fit for the data because it doesn't actually have linear correlation between the two. So to go with that, the regression line is only good for X values that are near the data. So based on this particular example, our X values were all something between 6 and 16. So I could only predict stuff that's near that. I would not be able to predict Y values for X being 1,000 because that's so far out of this range of values. The other thing, if there's no significant linear correlation, like technically the last example didn't, instead what I'm going to do is use my means for my best predictor. So either I'm going to use the mean of my X values or the mean of my Y values. So to go through that, let's try 2 examples. Using paired sample data of distances, which are given in miles, and fares, which are given in dollars, of randomly selected taxi rides, the regression equation is y is equal to 5 plus 0.3x, where x is representing that distance and y is representing the fare. So if it is found there is significant linear correlation and the mean fare is $12, what is the best predicted fare for a ride of 3 miles? So here, since we have significant linear correlation, we're going to use the regression line. So our y value, which is the fares, is going to be 5 plus 3 times the x value. So in this case, our x is a 3-mile ride, so we replace x by 3. So our fare estimate is 5 plus 9, which gives us $14. So we would estimate for a ride of 3 miles, we would pay around $14. But if I change this slightly and I say there is not significant linear correlation and the mean fare is y equaling $12, what is the best predicted fare for a ride of 3 miles? So here we're going to use the mean fare because there is not significant linear correlation. So what that means, the best predicted fare for a ride of 3 miles is our value of y bar, which is $12. Okay. So this line of best fit is only good if you have significant linear correlation. Okay. So I really just have one more example that we're going to do, and we're again going to utilize technology to help us. So listed below are the number of cricket chirps in 1 minute and the corresponding temperatures in degrees Fahrenheit. First thing we want to do is we want to find the regression equation, letting chirps in 1 minute be the independent variable. So essentially meaning this is going to be our x value and the temperature is going to be being the y value. So we are instead going to use Excel to go through this. So I've got all of my data here loaded into Excel. So we're going to go ahead and add that scatter plot and then go in and add that line of best fit. So select all the data, insert, go to the scatter plot, add that, highlight the data, add your trend line, and then click display the equation on chart and just move it into view. So that is going to be our line of best fit. And again, it's just out of order. 0.0564 is going to be the slope, and then the 23.17 is that y-intercept, which is the value of B0. So I've got that scatter plot added in, and so our regression line is our y values. We'll flip this order now, is 23.174 plus 0.0564x. So this is our line of best fit. Now part B says find the best predicted temperature at a time when crickets chirp 3,000 times in 1 minute. So I still need my line of best fit, so just gonna move that into view. Our value of y, which is the temperature, is 23.174 plus 0.0564 times x, which is the number of chirps. So I'm going to replace that by 3,000. And then rounding this to my nearest temperature, this should give you about 193 degrees Fahrenheit. Okay. Now the problem is, sure, I found a number, but if I'm thinking about crickets, they would not survive in 193 degree Fahrenheit weather. So in terms of what's wrong with this predicted temperature, this is unrealistically high. There is no way this is going to be the temperature outside. And the reason for that, if I go back to my scatter plot, my smallest number of chirps is around 79. And then my highest amount of chirps is 1114. So 3,000 chirps is so far outside of the range of these X values. So it doesn't make sense to plug that in. So here it's unrealistically high. These poor crickets would be roasted and toasted. So the value 3,000 is far outside the range of given X values. So this hopefully is pretty obvious to see that, sure, the temperature outside in no way, shape, or form can be 193 degrees Fahrenheit. So this is something you can clearly see we made a mistake for. The problem is when you're working with maybe money or like number of customers, you can't quite know what's unrealistic and what's not, which is why it's super important to recognize if the value you're inputting is nearby your data values. Because if it's not, there's no way I can use this to predict my Y value or predict my temperature. So you got to be really conscientious about your inputs and where your data lies to be able to make any type of prediction.